So in the last video, we looked at this question where we applied the method of joint to find the internal forces in each of the members. And in this video, we're going to apply the method of section. So let's begin. Now, the method of section is a very convenient way to get to your answer very quickly, or you can simply use this method to validate your answers for, say, for instance, the method of joint. Now, to recall what we did in the last video, the angles were 30 degrees there at the base, 30 degrees, 30 degrees across all. In terms of our dimensions, I'm just going to input the ones that are crucial for this question. So if we were to draw an imaginary line, as I'm doing here, then the dimension between R1 and that line would be 2 meters, and it's going to be the same across here, where between R2 and that imaginary line would be 2 meters as well, and across there, same, 2 meters and 2 meters. Now, we're going to start doing our analysis using the method of section. And one thing we have to ensure that we're aware of is that when we use the method of section, we need to make an imaginary cut, as you can see right there on the diagram. And that imaginary cut cannot go across more than 3 unknown members. So if you take a look here in yellow, that's one member that will go across. That's another member right there in the middle that will go across. And finally, that's another member that will go across. And if you don't know what I mean by saying going across, just follow that red dotted line and you will see where it only intersects 3 of the members on the truss system there. So let's now look at how we do our calculations. So here I have isolated the members that my cut went across, and I've taken the part of the beam to the left. We could have chosen the part of the beam on the right hand side and we would have gotten the same outcome. It doesn't matter which part of the beam we choose. So just like we did before, where when we take a cut or a portion of the beam, we're going to assume that the members are in tension. And what that means, you will find where each of the arrows at the end of the cut is pointing away from the joint. That's all that means, really. You will also notice that I've inserted some dimensions. So this here at the bottom, that's the 2 meter long, and it only goes to where that red line, that vertical red line, intersects. And if we were to apply some trigonometry, using our angle here, our 30 degrees, using opposite and adjacent, then if we do 2 cos 30, that's what led us to this 1.155 meters. So just to ensure that you understand how we arrive at those figures. The 4 newtons is just as is. So let's get into how we do the calculations now. So for our calculations, we have 3 equations that we're going to apply. So the first equation is to say that the sum of our vertical forces should be in equilibrium. So that means if we sum all the forces going upward, we should get the same result as if we sum all the forces going downward. So the second is the sum of all the horizontal forces. So this symbol here, that capital E looking symbol, it means the sum of, and FH is just for horizontal forces. So they should sum to give 0 as well, or in other words, they should be in equilibrium. And then the final equation that we will apply is the sum of our moment about any point should be equal to 0, or being in equilibrium again. So what that means is our clockwise rotation should be the same as our counterclockwise rotation. So now let's see how we determine which of these equations we apply and how we do it. So the values that we got from our previous calculations for R1, let's just jot that down. R1 was 5.75 newtons. And that will remain the same because, like I said, it's the same question that we're looking at, just looking at another method. So that's R1 equals 5.75 newtons. And R2, even though we're not going to use it, was 6.25 newtons. So that's R1 and R2. So let's find these unknown forces. So we have 3 unknown forces that we're going to evaluate here. The first one, as you can see, is F6 right here. We have F5, and this from our previous again was F2. So how do we solve for these? How do we determine if we are to use this equation, sum of the vertical forces, or the sum of the horizontal forces, or using the moment equation? Now, it's quite straightforward, really. If we have more than 2 unknowns, it means we cannot use that equation. And how we determine whether or not we have more than 2 unknowns? Let's say we were to use the sum of the horizontal forces. Well, we have the unknown component here for F6. That's horizontal component for F6 going to the right. That would be unknown. We also have the unknown component for F5 and F2. So basically everything that we're trying to find, they would all be unknowns. If we were to use the vertical component method, or the sum of the vertical forces, then again it would be the same thing. We would have 3 unknowns. So the only method at this stage that's most suitable is for us to apply the sum of the moments. And I'm going to show you how to do that now. When we apply the sum of the moment equation, we have to think strategically to make our lives easier. And what that means is we need to pivot about a point where at least 2 of our unknowns pass through. So if we look here, we can see where F5 and F6, they intersect right here at this joint. And I'm just going to label that joint as joint B or A, any letter. It's just for you to identify it. So right here, those 2 members, they intersect at that point. So the significance of that is when we find the moment, we're doing force multiplied by perpendicular distance. So that's the force multiplied by the perpendicular distance to that pivot point. So if right here, where those 2 members pass through, is our pivot point, then the actual distance of F6 from that point, its perpendicular distance, would be 0. So as a moment, then that would be 0. The same thing would be for F5 as well. That would be 0. So the only force or unknown force that would be having an effect on that joint would be F2. The 4 newtons again would be passing directly through that point. So once again, that would be 0. It would have no effect. So let's do that sum for that sum of the moment. So our system will remain the same. We will still say clockwise moment is equal to our counterclockwise moment. We have R1 and the perpendicular distance of R1, so that's our R1 right there. The perpendicular distance of R1 to that pivot point is 2 meters. And how you know that? If you were to just trace, I'm just really breaking this down just as you really get it fully. So if we were to trace, I'm going to use yellow, and I'm going to trace this path, and that's representing that line of action for R1. So that force, the line of action is along that yellow path. And I'm now going to just go across here to where that pivot point is. And this distance, it would basically form a rectangle, and the distance here would still be 2 meters. So we'd be doing R1 times this perpendicular distance there of 2 meters. So that's why we're going to use R1 times 2, and it's going to try to rotate this thing like so. So that's going to be clockwise moment. So let's put that down. Now at this point, that's the only force that's trying to pivot this system in a clockwise motion. The next force that we have is F2, and we're going to apply the same thing, but it's even more clear because you can see F2 intersects this vertical line here that measures 1.155 at an angle of 90 degrees. So that's a perpendicular distance. So what we'd use then is F2 multiplied by that distance of 1.155. So in this equation, the only unknown that we have now is just F2. So let's solve that. So therefore our F2 is going to be equal to 5.75 times 2 and all divided by that 1.155. So F2 is 9.96 newtons and it's positive, so therefore it's a tensile member. So already we have found the internal force for one of our members. So let's work out now for F5 and F6. So now that we have at least one of our three members, we have two more to figure out. And the question is, which of the methods should we apply again? Should we use vertical force components? Should we use horizontal? Or should we take the moment about a point? Now, we could have easily picked a different point to take the moment about that said point, but either way would have still two unknowns. So what we are going to do now, we're going to use resolving the forces vertically and horizontally, so that we get a good feel of each of the methods. So let's do that now. Let's take the sum of the vertical force components and they should be balanced. So forces going up should be summed to give same as forces going downwards. So let's see what we have. So the members that we have going upwards, we have our R1. So that's the reaction there to the left. We also have F6 that's pointing upward and to the right. And what's going downward, we have that 4 newtons and we have that F5 that's going downwards. So let's put these into our equation then. So on the left hand side, I'm going to use the sum of the forces going upward, and on the right hand side, sum of the forces going downward. So going upward, that 5.75. We also have the component there of our F6. So that would be summed to be F6 and sin 30 degrees, just like we have done before in finding vertical and horizontal component. So just in case you don't remember that, if it's the vertical component, it's just going to be force, sin, and then the angle. And if it's the horizontal component, it's just going to be force, cos, and then the angle. So that's what I'm doing here. So let's go across then to the downward forces, and for this one we have our 4 newtons, which we don't have to do anything to, it's just a vertical force, and we also have our F5, so that would be F5 sin 30. Now a very clever thing to do here to simplify this, because we have sin 30 that's common to our unknown forces, if we were to divide the entire set of numbers or the entire equation through by sin 30, then that would simplify everything massively. And remember that sin 30, it represents a value. It represents 0.5. So what we're going to do here at this stage to simplify this entire line is to divide through by sin 30. So we're going to divide each of those terms by sin 30. So our 5.75 divided by sin 30 or divided by 0.5 would leave us with just 11.5 plus F6 times sin 30 divided by sin 30 leaves us with just F6. And when we do 4 divided by sin 30, that's going to give us 8 and plus F5, because sin 30 once again will cancel sin 30. Now we can simplify those constant values, and if we were to do that, then we would end up with something that looks like this. F5 equals F6 and plus 3.5. And that's just us subtracting 8 from both sides. So that's what we're left with there. So that's one equation that we're going to come back to as soon as we do the horizontal force components, and it's going to be really simple once we get this bit done in a similar fashion. So let's do that. So here we're going to apply the horizontal force component, and they should sum to give 0. Now, just a quick look so you can recall what we are going to work with. We are looking for all the forces that's going to the right or to the left, and we're going to sum them so that they equal to 0. Now, this question is quite unique because F6 is going to the right, F5 is going to the right, and F2, which we have found, is also going to the right. So it means what's going to the left is going to be simply 0. So let's set that equation up. So this 0 is representing what's going to the left. We don't have any force components going to the left. So that's why that's 0. And then because we have already found F2, we can just insert F2 because we know its value. We don't have to do any force components. And also F2 is just an horizontal member. So it's only an horizontal force we will use there. So F2 plus F5 this time around is cos 30 and plus F6 cos 30. Now the same thing that we did previously to simplify this equation is we're going to divide through now by cos 30. So let's do that. So that would still be 0. This would be F2 divided by cos 30 and just plus F5 and plus F6. So let's just simplify this now. So since we already know F2, let's insert the value that we got for F2 previously. That was 9.96, and that will be divided by cos 30 and plus F5 plus F6. Now we're going to make F5 the subject here. So we're just basically going to rearrange this to make F5 the subject. So we'd just be subtracting F6 and the value that we get for 9.96 divided by cos 30. So that would leave us with F5 equals the answer for that bit, which is minus 11.5 and minus F6. So that's just rearranging equations there. So now that we have something for F5 and F6, we are going to do some substitutions, and the rest of it is going to be quite straightforward. So this bit that I'm underlining, that's what we got for the horizontal force component, and I'm going to just put beside that what we got for the vertical force component in purple, which was F5 equals F6 plus 3.5. So now, how we do the substitution? Well, it's quite straightforward. Since both of these equations are having F5 as the subject, then we can use either one to substitute what we have for F5. So, for instance, if we were to replace this F5 right there with what we have F5 equal to over there, then what we would end up with is this F6 plus 3.5 equals minus 11.5 minus F6. So right away, all we have in this equation is just F6 as the unknown, and we can solve that quite easily. So let's just group our like terms and rearrange. So we would end up with 2F6 equals our negative 11.5 and minus 3.5. So to cut to the chase, F6 would then be equal to, that's negative 15 over 2. So we get this as negative 7.5 newtons, and it's negative, so therefore this member is compressive. So that's F6 done. And then for F5 now, since we already know what F6 is, we can just simply use either of the two equations at the top, the one in blue or the one in purple, and substitute what we have here for f6. So let's do that now to find f5. So I'll just use the one in blue. So f5 is then equal to minus 11.5, and we're going to minus what we have for f6, which is negative 7.5. So just be careful with those double negatives there. So that now would leave us with a grand total of negative 4 newtons, and that's compressive, and that's what we get for f5. So that is all three unknown members. If you want another method, then just drop in the comment graphical method next, and if you do, then I'll do that next video, and until then I'll see you in the next video.